Okay, we're going to do the second part of whiteboard problem 25.3, which is to find the potential energy of the system. Okay, so this is what our system looks like. So we have our Q1, Q2, Q3, and Q4. So we've added this fourth charge, and then we need to find the potential energy of the system. Okay, and so we, things that we know. So we know all of our charges, Q1, Q2, Q3, Q4 is plus Q, minus 2Q, 3Q, and 4Q. And then we know lots of distances. We know R12 equals R24 equals R43 equals R31. So that's just going around the perimeter. All of those distances are L. And then we know the distances between R14 and R23 are going to be the square root of 2L, because those are the diagonals of the square. Okay, so our model is going to be superposition again. Superposition of potential energy, meaning that we can sum up the potential energy of between all the pairs that we can make in this square. So we kind of just did that. So we have 1 to 2, we have 2 to 4, 4 to 3, 3 to 1, and then we have the diagonals 1 to 4 and 2 to 3. So our potential energy total equals the potential energy between 1 and 2, the potential energy between 2 and 4, the potential energy between 4 and 3, the potential energy between 3 and 1, and the potential energy along the diagonals, which is 2 to 3, and potential between 1 to 4. Okay, so all of those are going to be K, Q, whatever, divided by the distance squared, right? So potential of a point charge potential energy, right, is K, Q1, Q2 over the distance between them squared. Just distance between them, sorry, not squared, because this is energy. Okay, and it's a vector, right? It's not a vector. Oh my gosh. So it's a scalar, so we're just adding these together. We don't need to worry about direction in this case. Okay, so we have, if we break this out now, we have K, Q1, Q2 over the distance between them, plus K, Q2, Q4 over the distance between 2 and 4. And we have K, Q4 times Q3 over the distance between 4 and 3. And K, Q3, Q1 divided by the distance between them, 3 to 1. And then we'll add over here K, Q2, Q3 over the distance between 2 and 3, and then K, Q1, Q4 over the distance between 1 and 4. Yuck. All right, so we'll factor out our K as a first step. Okay, and then we can plug in our values here. So Q1 is Q, Q2 is negative 2Q, and then we said our 1, 2 is just L. Okay, and then we have here Q2, which is negative 2Q, 4, which is 4Q, divided by the distance between 2 and 4. So that's this leg of the triangle, right? Or square, right? So that's just another L. And now we're on this term. We have Q4, which is 4Q, Q3, which is 3Q, divided by the distance between 4 and 3, which again is the side of the square, so that's L, plus Q3, which is 3Q, Q1, which is Q, again divided by the leg of the square, plus down here we have Q2, which is minus 2, Q3, this is across diagonal now, and then square root of 2L is the distance between them. And then we again have this other diagonal. So that's Q1, which is Q, Q4, which is 4Q, divided by, again, the length of the diagonal. Let's just make that a square bracket so it's a little more clear that all of that's going to get multiplied by K, and that will give us our potential and total potential energy. Okay, so every term here has a Q squared divided by L, so let's factor that out. Okay, so we have K, Q squared over L, and then we're left with, from here, the first term, we just get a -2. The second term gives us a -8. The third term gives us a +12. Fourth term, it just got a 3. Okay, and then down to here, we get a 2 times a 3 divided by the square root of 2, so that, and that's a negative, right? So -6 over the square root of 2. And then here we have 4 over the square root of 2. Okay, we do a little of this in our head. So this is -10 and 12. So 15 minus 10 is 5. And then we have 6 over the square root of 2. So I think we end up with -2 over the square root of 2, right? 6 over the square root of 2, negative, and 4. So I'm going to call that done. I mean, we can multiply that out as well, I guess. So 5 minus 2 divided by the square root of 2, 3.59. Okay, so if we want an exact answer, if that feels more satisfying, 3.59 is times K Q squared over L is our total potential energy. And there we go. So again, let's take a look back that we have the what we need to find, what we know. We have our diagram, we have our model, we have our general equation. We've done written out the sort of general equation, then plugged in the values, then did our rearranging to get the final answer. Looks good to me.